So let's continue our discussion on reducing the logical effort. Right, that's where we were last class and last two classes, in fact. So basically, to summarize what we have discussed till now is a static CMOS logic is like this. There is a PMOS pull-up network. There is an NMOS pull-down network, and the output is in between the two. Then, in order to reduce the logical effort, of course, the same inputs go to both. Right? This has very high logical effort because of the PMOS block. Therefore, we said let us take the PMOS block off completely. Keep a PMOS transistor which is on always. However, this has to be a weaker transistor than the NMOS, right? And you have only a pull-down network, right? This is my static CMOS. In today's class, I'll tell you why this is called static CMOS, right? Because we have something called a dynamic logic later. So this is a pull-down network, and we said that this is called pseudo NMOS because it's mainly NMOS logic. We have just one PMOS transistor. PMOS is really not used to implement any logic function, right? Therefore, it's called pseudo NMOS logic or ratioed circuit. Ratioed circuit because unless the ratio of WP by WN is correct, this circuit cannot even function, right? So problem is VOL is greater than 0, right? WP by WN is as proportional to VOL. So this ratio is critical, and therefore it's called a ratioed circuit. Right? And of course, there's also another problem. There is static current when the pull-down network is active because the PMOS is always turned on. Right? So, in order to overcome this problem, we came up with the idea of implementing a cascade voltage switch logic. We just said that all you have to do is have two pull-down networks. Of course, you have more area now. On one side, you implement the function f. On the other side, you implement the function f bar. Then the opposite side of where the PMOS and NMOS are fighting will ensure that output is logic low, and therefore it will just turn off the PMOS transistor and prevent any static current. Right? This is called CVSL logic. Right? Problem is, of course, you require A and A bar to be available, and no doubt you have more area in general. Okay? So there are certain advantages in this, and it's useful in certain places, but you're doing this at the penalty of throwing in more transistors and hence more area and also therefore more power. Okay, so you just have to keep these disadvantages in mind. You get Y bar and Y. Okay. So what I really want to do now is I want the benefits of this CVSL logic, but I still don't want to put in so many transistors. Okay, it turns out that is possible by doing what is known as dynamic circuits. So let us just quickly look at what is the philosophy behind a combinational circuit. Suppose I have an input making a transition here and then here and then here. The output will follow with some delay, it will follow exactly this. Right? The point being that I can make a transition at any point in time and my static CMOS circuit will respond with some delay. Right? But most of the time, what we have is you have a system which is going to be, you have inputs, primary inputs, primary outputs, and you're also going to drive it with a clock phi. Right? They're basically you're going to have flip-flops which are going to sample the inputs, hold the input constant during the clock. Then you can evaluate, and you have some implicit constraints are there on when the input can make transitions so that the outputs will appear without any error. Implicitly, these constraints are there in a system. So why not we exploit those constraints? Okay, that's the basic philosophy here. The second thing is, if this input made a transition and this steady state value just remained forever, okay, then this steady state value would also remain forever. As long as my power supply is connected, both of them will remain in that state forever. Right? These two conditions we are going to exploit, and we are going to compromise so that we get better logical effort but do away with all those problems that we had in the pseudo NMOS circuit or the CVSL logic. Okay? So what we do here is, instead of my pseudo NMOS logic, which was simply connected to ground, right? The gate was connected to ground always, pull down network. I say, don't connect it to ground, but connect it to the clock. Phi. Okay, I have a clock in the system anyway. I'm going to connect it to that clock. Right? So what happens here? My clock is going to look like this. Okay, a realistic clock will have some finite rise time. What happens when my clock is 0? PMOS is turned on, and therefore the output is Y will be logic high. Correct? So my Y output is going to remain high here. Now let's assume that my pull down network never turns on. Okay, the input combinations are such that they never turn on. Okay, there is no transition happening. My inputs are here, right? Some different number of inputs. And it turns out that the pull down network is never activated. The input never makes a transition. So what will happen the moment my clock turns off or goes high? What will happen to a PMOS transistor? Yeah? It's going to be off. So what if the pull down network is never going to be turned on in that state, based on that assumption, and the PMOS also now turns off? What state is my output in? High impedance, or it is going to float. So I will represent high impedance by a dotted line. Now, question is, will this be at VDD always? Clearly the answer is no, because now there is a leakage path through the pull down network, right? Let me replace this pull down network with something that we know. I am going to connect it to a single NMOS transistor A, right? I am going to make an inverter. So this I will connect here. Let's say this is the pull down network. Dynamic inverter is what I am constructing, right? Clearly, and what are the sizes now? NMOS will be, NMOS should be how much? Half. Why? No. So, okay, let's assume that the minimum size is 1. Yeah, so it is 1. Similarly, this PMOS size we'll fix later. Okay. So now there is a leakage path. When I say output Y is floating, there is a leakage path through this NMOS transistor through the subthreshold leakage. And therefore, strictly, this VDD will actually drop slowly with time until the next clock comes, the next falling edge comes and takes it back to VDD. So here, this will again go back to VDD. Right? This is high impedance. So why is this circuit called a dynamic circuit? Because when my clock goes high, that is when I'm going to allow this circuit to evaluate the particular logic. Okay, these two clock phases I'm going to call as pre-charge and evaluate. In the pre-charge phase, all that the clock is doing is taking the output to 1. In the evaluate phase, the clock is turning off and it will allow the pull down network to pull the logic low if necessary, depending on the input combination there. Right? So the circuit, instead of being a regular combinational circuit where it can evaluate in any phase of the clock, we are now putting a restriction that this circuit can work only in one phase of the clock. That is when the clock goes high. Okay. So why is this called dynamic now? Let's assume that I slow this clock down sufficiently. I make the clock period 1 hertz. Right? 1 second I'm going to, my time period is 1 second. Clearly, in 1 second, this output Y, even though my input is 0, right? My output is supposed to be 1 forever. Correct? But because the time period is so large, it can leak out. And the output eventually can go below. If you just allow this to go on and on, it will eventually go below the threshold of the, of a gate, VTN, and then it will effectively become logic 0. So it's called a dynamic circuit because the output is dynamically floating on a capacitor and you can evaluate it only in a particular period of time. Static CMOS logic will hold its value as long as the power supply is on, even if your clock is down to a frequency of 1 hertz. So that's why that is called static logic and this is dynamic logic. Okay? Yeah. No. That's the whole point of doing this exercise was to get rid of my PMOS logic because I want to reduce logical effort. If I pre-discharge to ground and pull up through the PMOS logic, I am just losing that entire advantage. NMOS inherently is smaller for the same drive strength. Therefore, I have to do only pre-charge and then pull down logic. In this example, both are off.
So like there will be leakage from VDD to output, right?
Correct. Absolutely. So you must be very careful because again you have to size this correctly. Now the logic is, why should I size my PMOS transistor if that's not going to take part in the logic evaluation? I will make that also 1. So you're right, there will be some sort of a fight of leakage between these two. And since the NMOS is now going to be stronger, right, it will be closer to 0, that state. You're right. Okay?
So if you make the PMOS little stronger, then even if evaluate phase comes, like the voltage increases, it will be still on.
Yeah, correct. That's true. Okay? So now let's consider, this dynamic inverter again, but we'll Now allow the input to switch a little bit. So this is my clock 5. So let's say my output, my input, right? So this is again precharge evaluate. Precharge evaluate. Let's say my input was 0 and in the evaluate phase it went high. Okay, this is my input transition. So how will the output Y now look like? In the precharge phase, A is turned off. There is no problem, right? So therefore, my output is going to be logic high. Now, at this point, my clock is turning off. So between point 1 and 2, what will be the state of the output? High impedance. So I am going to represent that by a floating line. Of course, assuming that this is reasonably close, fast time, it will not fall too much. I'm assuming it's going to be very close to VDD, right? Now the input is going high. So what will happen to the output? It can fall, yeah, right? It will fall like this and then remain until the next precharge phase comes. Correct? This. So now, what is the problem that you see here first of all? Both are on. So in the precharge phase, I have a constraint that the input cannot be high. The pull down network should not be active, right? So for that, what I do is I just add another transistor here called a footer transistor, collecting the same clock. So when the clock is 0, it's in precharge phase, PMOS will be turned on and the NMOS will be turned off. Okay, this is my footer device and this is my, let's call it a header device. The NMOS transistor, footer NMOS, is off during the precharge phase, right? It's the PMOS that is turned on. Therefore, now input A can be any value because there is no path to ground because I have cut off that series path, right? And therefore here there will be no problem. Okay, if there is footer device. Clear? Now I will give you another interesting scenario. Let us say that this input went high and then it fell here. What will happen to the output here? Yeah? So the output is 0, right? When input A went high, output went to 0. Now my input fell. There is no path to pull that Y up back to VDD. And therefore this will just remain at 0, right? So there is a very serious constraint here that this kind of a circuit can tolerate only a rising input, right? Or a falling output. You have to design your circuit so that the inputs during the evaluate phase do not switch in the other direction. It can go from low to high, no problem. But the input cannot go from high to low. Right? So what I'm saying is, suppose my input A was like this, right? With a footer device during pre-charge, my input A can be high, no problem, right? And then my clock sort of turns off the header device and it goes to evaluate phase. What will happen? Immediately my output Y, which was 1, will fall, right? So if this is high like this, and let's say it falls somewhere in between, as soon as this clock goes high, this will result in the output falling. Now my input after some delay falls, but nothing can pull my output back high. Therefore, this transition is not allowed. Okay? Input cannot fall in eval phase. Okay, so therefore, of course, it's very clear that it can be used only in certain conditions, certain constraints. If you have no control over the inputs and you have to guarantee that the circuit works for any transition, well, you cannot use this style of logic. Use the static CMOS logic, you have lower logical effort and you have those problems. But at least logically it will work. So under the constraints where you are able to impose these conditions, like in a DRAM circuit, the place where these circuits is used quite often is a dynamic random access memory circuit. I won't have time to like show you exactly what happens, but it's effectively this dynamic NOR gate is what gets used in a DRAM memory. In those places, I can impose these constraints and therefore use the logic, and therefore it's very fast. Okay.